Acid-base titrations were first introduced last year in grade 11. They occur when a volume of titrant is added to a known volume of a sample. Addition of titrant continues until the reactant in the sample is consumed by the reactant in the titrant. This is known as your equivalence point. Typically, we use an indicator to detect this change, such as phenolphthalein. And when the indicator changes color, in terms of phenolphthalein, that would be from colorless to pink, it is called the endpoint. To quickly review these types of calculations from last year, if we had a sample of NaOH 0.2 mole per liter used to titrate 25 mils of HCl, the equivalence point is reached when 10 mils of NaOH has been added. Calculate the concentration of HCl. The first thing we need is a balanced chemical equation. NaOH plus HCl is going to make our salt, NaCl, plus water. We are given volume of NaOH, and we're given the concentration of NaOH. So the first thing we want to do is find the number of moles. And that is going to be concentration times the volume. We're going to plug in our numbers here. 10 milliliters, we got to change to liters. That would give us 2 times 10 to the minus 3 moles. Because our reaction reacts in a 1-to-1 ratio, that means that the number of moles of HCl that we have is also 2 times 10 to the minus 3 moles. Finally then, we have the moles and we are given the volume of HCl. We can find the concentration of HCl by taking moles divided by volume, plugging in our numbers. Remember again, volume needs to be in liters. That is going to give us a concentration of 0.08 moles per liter, or in IB terms, moles per decimeter cubed. There are 4 types of titration curves that you need to know. The first one being strong acid and strong base when they are titrated together. An example of this would be like our last titration, HCl plus NaOH reacts to give NaCl and water. This titration curve looks like the one pictured here, where we have pH plotted against volume of base added. Initially, at this point here, we start at a very low pH because we are starting with all acid and no base added. So it's going to be around pH 1 because it is a strong acid. The pH is going to gradually increase until we reach our equivalence point. And our equivalence point is here. It's halfway between these 2 points between 1 and 4. So in this part 3, there is a very sharp jump in pH at equivalence from pH 3 to pH 11. After equivalence, the curve is going to flatten out at a high value. And this is because now we have more base than we have acid. All the acid has been consumed. The pH at this point here is going to be the pH of the strong base. Because we have a strong acid and a strong base, the equivalence point happens at pH of 7. The second curve we're looking at is a weak acid and a strong base, such as ethanoic acid with sodium hydroxide. Now again, the shape of the curve is very similar to the last one, except now we're starting at an initial pH that is much higher because we have a weak acid. It's going to start around pH 3. The pH is going to stay relatively consistent until equivalence. Within this region here, When we add base, there's very little change in pH. It's acting like a buffer, so we call this the buffer region. There is then a jump in pH from about pH 7 to pH 11. The jump is not as sharp as for a strong acid and a strong base. And after equivalence, we are going to flatten out again at a high value, which will be equivalent to the pH of the strong base. The pH at equivalence, because we've got a strong base and a weak acid, is going to shift that pH higher to greater than 7. The third scenario is a strong acid with a weak base. This is, again, pretty similar to the last scenario, except now we have a strong acid such as HCl and a weak base such as ammonia. Initially, we're starting at a very low pH because of the strong acid. Again, stays consistent throughout this buffer region. There's a jump in the pH from about pH 3 to pH 7. And then after equivalence, the curve is going to flatten out. The pH will be lower because this is a weak base. The pH then, because it's a strong acid and weak base, is shifted down so that the equivalence point happens at a pH of less than 7. The last scenario is if we've got a weak acid and a weak base, such as ethanoic acid and ammonia. Now this curve is quite different. It looks much shorter. It's very hard to define. So let's go through each point again. We're starting at a fairly high pH because of the weak acid. Addition of base causes the pH to rise steadily. The change in pH as we reach the equivalence point is much less defined than other titrations. And finally, after equivalence, the curve flattens out, but again at a lower pH because it is a weak base. The equivalence point for these titrations, very difficult to identify.